Sziasztok mindenkinek! Hi to everyone! This will be the first series of the Ansys Static Structural course. This is a beginner course. In the first presentation, I will talk about the introduction into these finite element methods. Often I will recall this as FEA, which stands for Finite Element Analysis. In this first presentation, I will try to give a quick tour how these static structural simulations work. Generally speaking, how the numerical simulation work, why do we need them. We will start from the very beginning, but I will not delve into the mathematics of these calculations. Instead, I will try to focus on its logic, on its usual problems and how to avoid them. So basically the whole thing starts with designing a part. When we design a part, usually we do that in a CAD program. We get a CAD model. We oftentimes see that this CAD model is easy. For example, a bolt. It is like a threaded bolt or a threaded anything. The thread can be calculated pretty much easily with analytical approaches. This is taught in the university a lot of times. For example, the thin-walled pressure vessel can be also calculated analytically with very high accuracy. But when it comes to the more complex CAD models, for example, in the Prometheus rocket we have the Redex couplers, or we have the nozzles, which typically have a much harder design, a more complex design. We tend to try to use simplifications to the geometry, which might enable us to use analytical approaches. But oftentimes we stick with finite element method analysis, or FEA. So basically this is the journey when it comes to usually to the FEA solvers when we are deciding to design a part. Basically what finite element method is doing is that we try to solve this DE, which stands for differential equations, and PDE, which stands for partial differential equations. We try to solve them numerically. What does it mean? So basically, let's imagine a basic differential equation where we have usual function which depends on time. Oftentimes these differential equations can be solved. It is taught how to solve these, and oftentimes it is good if you can solve them analytically. But some equations are very hard to solve, actually most of them, and they are much faster to solve with numerical solutions. Basically what it means that when we solve differential equations with analytical method, the dt time is infinitely small. When we are solving differential equations numerically, the dt time is like a number. For example, let's use now 0.1 seconds as a number. We will try to kind of calculate the function based on these steps. So they will not be infinitely small, and as an example we see here the so-called explicit Euler method. I will not delve into their logic, but the main thing is that we have with red we have here the original function, and we are trying to go closer and closer to the original function with different numerical methods. With purple we have the explicit Euler method, which for example uses the 0.1 seconds. If we take for example 0.05 seconds time step, we see that it is much closer to the original function, but it is actually here pretty far. So the question that comes to all of our minds, that how can we then calculate everything like actually good, close to the reality. Basically, explicit Euler method gives this basically we can calculate the original function with this. We just need to get a small enough time step. This is actually pretty similar if we think back to the analytical solution, because there the dt is infinitely small, so kinda if we get the dt to infinitely small, it will give back the original function. The question is always that whether it needs to be this hard. Do we need to get this kind of a resolution? Uh, when this question comes to our mind, usually we will try to search for better solutions, and like in a basic differential equations we can use like a Runge-Kutta method, which have several orders, like second order, fourth order, and there are infinitely more orders. They are all basically the same. They are an improved version of the explicit order method, and basically that's it. So I will not talk about this further. I think everyone understood its logic behind this. So we are trying to calculate the differential equation in discrete points. This is the most important thing. When we are trying to solve these differential equations on geometry in, for example, 2 or 3 dimensions, it is called not a simple differential equation, but a partial differential equation. Uh, when we get to the point where we need to use partial differential equations, oftentimes we see that these differential equations are extremely rarely solvable fully. For some instances, we can estimate them, that how they are going, but for like any geometry, it is impossible to solve them. Basically, how should we proceed with solving these partial differential equations? Uh, Basically the same thing. Before, in the differential equation, we try to estimate the function with dividing the time into more steps. Here we will do the same thing. We will divide the space into some parts. These parts, I will now call them cells. So this is a cell. Yeah, I think we can move on through this. It is not that interesting. Yeah, so how should we mesh our CAD models, or what is the mesh? So before I told you that that thing was a cell. It is actually called everywhere a cell, but the cells can be different in geometries. For example, here this cell is a quadrilateral cell, which is a 2D cell. In 3D, we can have, for example, hexahedrons and stuff like that. On the corners of the cells, there are the so-called things nodes. It is important that the nodes are in the corner only at the typical finite element analysis. Later, maybe in some future courses, I will talk about the finite volume analysis. They are for CFDs. The nodes there are in different places. So the nodes are in the corners. Of course, it is evident that some elements have more corners per element, of course. This we will just remember this for the future, because I will talk about this in a bit. So here are some example meshes. This is a nozzle of a rocket engine. 2D analysis, it's for thermal simulations, and this is the forward closure of a rocket engine. This is a 3D periodic analysis. So of course, that I talked about in the, for example, Runge-Kutta method and the Euler explicit method, a question comes to our mind. How could we even estimate that what would be the correct mesh resolution if we don't know the original function. It is a very important thing because for most of the cases where we study, for example, in what we study in university, we see that yeah, it's we know what is the solution and we try to get the solution right. Here we don't know the solution. We don't know whether our simulation is correct or incorrect. This is why an analytical solution is always a good relaxed point kinda thing because it gives our confidence that our simulation would be good. But in most of the cases, there are no existing analytical solutions. So what we need to like as a guidance. So here is a cell. Here are the nodes. The nodes are so-called computational points of the solver. In these nodes, the solver will calculate basically its equations, whether it's a static structural solver, whether it's an explicit dynamic solver, whether it's a thermal simulation solver. They are basically the same. So here is one node, here is another node. How the other node, for example, this will know what the before one calculated. So basically how it operates is that it will make an interpolation between two nodes and then calculate the things that it needs to. I think everyone understands now that why it can be a problematic area if the mesh resolution is not enough. Because the interpolation will be enormous, and when our forces are very high, for example, or our stresses are very high, we call it basically it's a huge magnitude thing. The gradient will be very high, and these very high gradients are a bit hard to capture. So for them we will need some kind of help from the mesh, which we call refinement. In general, kind of sayings, this is coarse and this is a refined mesh. Also, the mesh are sometimes in literature called grid. So we refine the mesh and hope that it will be better. Now that we have our mesh, our job is to define the boundary conditions. So as I told before, we're now only going to talk about static structural simulations. So the static structure criteria are basically the whole defining thing about these simulations. It means just nothing is moving. So when nothing is moving, it means that the sum of all forces is zero. And basically what it means that if we define a pressure, force, acceleration, vibration, or random vibrations, we need to constrain our system in the way that it will not move. As constraints, we can use fixed support, frictionless support, and so on, but we will talk about this when we will use the software. Of course, as learned in the differential equation courses like in math, we need some initial conditions, which oftentimes can be like some profiles. For example, temperature profile. We have some factors which can ease up our simulations computationally. They are the symmetry conditions usually. There are 2D axis symmetry planes, periodic regions, and probably some more in the newer versions. So here are some examples of how it looks if we are defining these boundary conditions. You can even import pressures from CFD. So basically, it is limitless what you can do. Once we've chosen our solver, which I will cover in the use series when we will actually use the Ansys static structural, there are some solvers. Basically, this is not as a complicated solver thing as, for example, in CFDs, but it is important because these simulations work basically of a very huge memory base. These memories are stored in your RAM, and basically the problem is when your mesh gets really high, like in element number. The element number means how much elements you have. A problem comes to us that the RAM is actually starts to get full. And the reason for this is that it operates with huge matrices, and some solvers tend to ease up these matrix-based solvers with creating more iterations and not a direct approach. This is the name of the two main solvers in Ansys static structural, the iterative based and the direct based. The direct, of course, can be much faster, but it needs a lot of resources, sometimes for big meshes. Under big meshes, I usually mean like above 1 million elements. So I talked about how can we check if our mesh is good enough, because like before we see in the picture a very good colored picture about our von Mises stress contours, and we don't know if it's good. How can we know if this mesh is good? We don't have a solution for this analytical solution. We just need kind of hope that it is good. For this comes to have the grid dependence test. The grid, as you might remember, it's the mesh. We will try to refine our mesh and see that how for example, for our point of view, now the most important thing is like the von Mises stress, how this stress changes. I'm interested in now that how this stress will change based on the refinement. And we can see that we refine, and basically the maximum stress is not changing by much. It is important that it will always change. And this change is caused by some numerical errors. If you have any question about this specific grid dependence test, you can contact me in Discord anytime. I will try to answer your questions. So basically, when we did this grid dependence test, as you could see in the slide before, there were some higher von Mises stresses when we refined our mesh even more. And if we will refine our mesh to the infinity, there can be some problems with that one. So as you can see it here, this mesh, you can not really see the mesh, but believe me that it is very fine. We can see that the whole part has like almost at minimum 6 safety factor, and in a very small area it has a very low safety factor, 0.5 safety factor. And when it comes to this, of course we cannot say that this part will fail, because when we zoom in we can see that this numerical error is very small. And of course question arises that why these solvers make such errors. It is not a big problem, because like everyone can see that it is under 0.05 millimeters. This is the first thing, and the second thing is it is due to the poor definition of boundary conditions. So when we define the boundary conditions, we define it on an edge and or a surface, and when we define them, it might be that one corner receives enormous amount of stresses, and due to this it kind of fails there. This is not good for the overall solution, but when our mesh is refined enough, it is almost impossible to see its effects on the other elements. So these are some phenomena which we can like sometimes see. in this kind of simulations, but I mean, with basic logic, they all can be like figured out that why they are happening. Yeah, so thank you for listening to me, and the next presentation will be not on PowerPoint. Instead, it will be held with the Ansys structural, and we will probably I will upload this presentation too in Discord, and then we will see that maybe I will try to cover almost everything there. For example, I will start with that how the whole simulation software looks like, what is what, and which is which. So probably the next session will be around 30 minutes long, but we will almost cover all the things from the creating the geometry to the end where we will simulate make a static structural simulation of a part, a 3D part. Thank you. Bye.